So thanks so much. I'm going to talk about selecting a research design this morning, and then I'll lead the experimental session on writing a pre-analysis plan, which will draw on some of the ideas from this presentation this morning. So as Alex said, I'm an assistant professor at UCLA. I primarily use field experiments and survey research in West Africa, particularly in Nigeria, to study the causes and consequences of violence in developing countries and what we can do about them. And so thinking about the RT2 roadmap, yesterday we had a kind of overview of open science practices and pre-analysis plans and some of the ethical ideas behind open science practices. And today we're going to focus kind of up here in the upper right-hand corner on pre-registration and pre-analysis plans again. And then this talk for the next hour is going to focus on power planning or selecting a research design and thinking about how we should compare different research designs that we might want to implement and how we should think about evaluating them before we write them down into a pre-analysis plan and pre-register them. Sorry, I just have to switch. Figure out how to switch slides here. Okay, there we go. Can you see these? Yeah, okay, great. So this is based on some joint work with Alex Kopic at Yale, Jasper Cooper at UCSD, and McCartan Humphreys at Columbia and the Weser Bay in Berlin. What I'm going to talk about is motivated by the problem that we face as researchers as we're developing our studies, which is that we're faced with dozens or even hundreds of questions each time we run a study. So we have to ask ourselves, how many people should I interview in my surveys? How many of those people should be men and how many should be women? How often should I interview them? Do I need to have a baseline, an end line, a midline, a second end line? Should I assign 2 or can I afford to assign 3 treatment arms to explore different variants of a treatment? Is it important in this case to use block random assignment, or can I get away with not collecting a baseline to have to do that? How many items should I include in my outcome index, and how should I index them? How should I trade off between the length of the survey and the number of respondents that I can interview if I have a fixed budget? Should I use robust standard errors or cluster robust standard errors? Should I control for emotions in my regressions, or am I at risk of post-treatment bias? Is it okay to drop people who didn't respond, or is that going to introduce bias? And to where can I generalize these results? So this presentation is about how we make these decisions in the course of our research, before we write our pre-analysis plan, and when things go wrong after we have registered our pre-analysis plan and we have to change tacks. And I should say, as we're going through, feel free to post a question, and Alex is going to interrupt me because I can't see the video, but happy to be interrupted at any time if it's going too fast or if you have any questions. Okay, so in order to make all of these choices in our research, we really need 2 things. First, we need a language for describing research designs that provides us a tool for being able to say what are the important components of this design, and then lets us evaluate that design according to criteria that we care about, such as power, but also bias and other things that I'll talk about. The second thing that we need is, once we have written down a language for research design, how do we choose among possible research designs? So each of these questions that I outlined implies a set of different research designs that I could select among. And so I need to be able to write down each of those designs and then have an algorithm for choosing among them. And so in the talk, I'll develop a language for research designs, and then I'll put that into an algorithm for selecting. So there's a couple of existing languages for thinking about research designs that are really helpful. The first is graphical models. So directed acyclic graphs, or DAGs, you may have heard about, are a really useful first answer to, like, what is a research design and how can we write it down. So I'll just go through this DAG in particular. I think that the details aren't especially important here, but the what a DAG does is it represents the causal variables in the system that we're trying to study. And so in this DAG, we're thinking about an experiment. So one of the causal variables we have is random assignment. We just labeled that Z. In our random assignment, we are going to use block random assignment. So we're going to divide up the sample into subgroups that are really similar. And then within those subgroups, we're going to randomly assign people into a treatment. So that second causal variable is a covariate that we're going to use in that blocking scheme. So we'll call that X. Then we have an outcome, Y, that we're interested in. We're interested in the effect of Z on Y. And the last causal variable that we have is some unknown heterogeneity. This is something that we just can't, we won't be able to measure through our surveys, but we know that there are other factors in the world that are also causing Y. So DAGs represent the causal variables and also how they are and are not related to each other. So each of these arrows represents a claim that I'm making as the researcher about how these are related to each other. So I'm claiming that Z is related to Y, and that X is related to Y, and that X is causing Z. X is causing Z because I've chosen to use block random assignment, so I've made sure that that's true, and I believe that X also may have an effect on Y. The outcome may differ depending on values of this pretreatment covariate. I also think that Y is going to be impacted by my treatment, and that Y is going to be impacted by this unknown heterogeneity in the world. One thing that I have also said is that U doesn't have an effect on Z. So there's no arrow from U to Z, which is an assumption that I'm making about the fact that this unknown heterogeneity isn't affecting the random assignment. That's a claim I'm willing to make in this experimental design because I'm randomly assigning Z, and so I know it's not related to any feature except for X because I use that in blocking. And so one of the valuable ways that we can use graphical models like this is we can say, I know that the treatment assignment Z and its effect on Y are not confounded by unknown heterogeneity in the world because I'm assuming that there's no arrow here. And so we can use, if someone else provided us with this graphical representation of the design, we could say, I know that this research is, under these assumptions, is not biased by this unknown heterogeneity because there's no arrow here. And so then we could assess whether we believed that claim. We can't assess, though, from this graphical model, the statistical power of this design. And the reason for that is that we don't know how. We know that Y is causally affected by Z and X, but we don't know how. And in particular, we don't know what the expected effect size is. And so if you've ever used any online statistical power calculator or any tool in Stata or R, you always have to provide an effect size. And it turns out you also are implicitly providing other information like whether the effect size varies by other factors, whether there's heterogeneous treatment effects. So a second language for writing down research designs is structural models, which do provide this information. So parametric structural causal models answer this challenge by putting a functional form on the relationship between these causal variables. So these also define what causal variables exist. We're defining here in this first equation that there's a causal variable Y, and it's related to Z, X, and U. So that provides a lot of the information that was in the DAG just a second ago, but it also provides this parametric relationship. And so in particular, we are making the assumption here that there is an expected effect size of 0.1, and that there's a linear relationship between Z, X, and U and Y. We've also said that, we've also written down some of our assumptions about the distributions of X and U. So X is a binomial random variable, so it's zeros and ones with a probability of 1 of 30%. U is this unknown heterogeneity that we defined, and that is a standard normal random variable. What isn't on here is any part of our researcher, what we might think of as our research design, which is how we randomize the treatment, how we select units into the study, and then what we're going to do with that data to analyze it, the data that results. So again, these two languages for writing down research designs are really useful. We can learn lots of things about them, but there's a need for more structure that provides information about what we as the researchers are going to do in this causal world that we've defined. And so what we've developed is a language for research designs that has 4 components that take many of the features from DAGs and structural causal models and add to them all of the choices that we make as researchers that are going to allow us to assess different choices that we might make as researchers. And so there are going to be 4 components of a research design in this framework: a model of the world that's going to be very similar to the structural causal models that I just outlined. An inquiry about the world, so that's going to be our research question, that is a question about the world that we've defined in the model. And then we're going to have the data strategy. That's all of the choices that you make as a researcher that yield data. So that's going to be things like your random assignment strategy. And then your answer strategy. And that's going to be all the things you do once you receive the data onto your computer, between getting the data onto your computer and publishing a paper. And so that's going to include your estimation strategy and how you choose to cluster your standard errors, but also things like how you visualize your data and how you decide to write it up into the paper as a function of different possible realizations of the data. Okay, so we have these 4 features, M, I, D, and A. So I'll outline each of them briefly. So the first is this model. So this is the theory of this system that we're trying to study in the world. So similar to DAGs, this is going to define what causes what, but also similar to the structural, parametric structural causal models that I defined how they're related. So we're going to write a function for how these causal variables are related, what effect sizes there are, what the functional forms are of each of these variables. We're going to define how the variables are distributed, so similar to how we defined that X is a binomial random variable and U is a standard normal variable. Those are going to be very important to the properties of our research design, and those are going to be guesses about how the world works. Similarly, we're going to define the correlations between variables, and then the kind of sequence of events of this system. And that just means in what order variables cause each other. So Z, our treatment variable, is going to cause Y, our outcome, and that's going to cause some other outcome, Y2, after that. So our model is the theory of the system under study. Our inquiry then is a feature of that model that we want to measure. There are a number of different kinds of inquiries. There are causal inquiries, things like the average treatment effect. It's the average difference in the outcome between a treated condition in the treatment variable and a control condition in the treatment variable. And we might have a descriptive inquiry, the average value of a variable. So going back to the DAG, a causal inquiry is going to involve 2 variables. So that's differences in how do differences in Z cause differences in Y. And a descriptive inquiry will just be a function of Y. So for example, the average value of Y, what's the average proportion of people who say today that they're going to vote for Joe Biden? Okay, so we have a model of the world, and then we have an inquiry, which is our research question about the world. Then we're going to define all of our interventions into the world to learn an answer to that inquiry. So the first piece of that is our data strategy. This is every procedure that we use to gather information about the world. And there are going to be 3 different categories of data strategies. The first is our sampling procedure. This is everything we do to select units from some population. So in the model, we've defined a population of units. These might be all of the people in Los Angeles County, might be all people living in the United States, it might be all districts in Uganda. From that population, we have to decide how units are going to get into our data set. So we have a sampling scheme. So that might be sampling precincts, voting precincts in Los Angeles County, and then randomly selecting voters who are registered to vote in that precinct. That might be our sampling strategy. And then we're going to conduct a survey of those people that we selected. So there's a sampling strategy. How do we select units into the study? Then there may be random assignment that randomly assigns some people to a treatment condition, some people to a control condition, or some people to a placebo condition, and some people to treatment 1, and some people to treatment 2. Or there might be, random assignment might be that everyone gets the same condition. The third piece of it is measurement. So once we've selected units and we've possibly assigned them to different treatment conditions, then we're going to conduct some measurement. This might be conducting a survey. This might be collecting administrative data. What is the procedure that we use to get outcome measurements from the units that were assigned into the study? So that's our data strategy. That's all of our interventions out in the world to cause data to appear on our computer. And then we have an answer strategy, which is what do we do once we have the data on our computer to produce an answer to that inquiry. So if our inquiry is the average treatment effect, our answer strategy is how do we take the data and produce an estimate of the average treatment effect, and then how do we present that to readers in our paper. So we often think about an answer strategy as just our estimation. We just think about like we're going to run a linear regression with cluster robust standard errors. But actually a lot of these other procedures turn out to really matter for the properties of our research design and what kinds of decisions readers will make on the basis of our paper. So that may include data cleaning, data transformation, then estimation. But then once you have estimates, how do you visualize and then how do you interpret those results? How you visualize and interpret the results often depend on the results of the data. And so we want to think about what different visualizations might we have obtained and what interpretations might we have made depending on how the data come out. And those procedures, depending on how the data come out, are going to determine the quality of our answer strategy. I've outlined here quantitative data collection procedures that might go into your answer strategy, but there's nothing special about this framework that's focused on quantitative analysis. We have also defined in our paper qualitative data strategies that can be implemented in this MIDNA framework. We illustrate how to declare a design for process tracing case studies and qualitative comparative analysis, QCA. It's exactly the same idea here with the answer strategy. These are procedures for taking information that we've collected through some intervention into the world and then yield an answer to our research questions, just that the answers are not a quantitative answer. Okay, so we have MIDNA. So I'm going to now represent a DAG for our research process and talk about it for a second. So in our research, in this research design, I've defined 4 pieces. The first is the model. The second is the inquiry. Third is the data strategy. And the fourth is the answer strategy. These are procedures. Each of these procedures lead to a realization. So we can think about a single realization of the model, which is a data set that's constructed under this model. And from that simulated data set, and I'll show you how we simulate that in a minute, we can construct from our inquiry an answer to that question under the model. And so this might be an average treatment effect of 0.1. So under our assumptions about the expected effect size, we can calculate the answer to our inquiry. Then this is all kind of theoretical. This is what these are our expectations about how the world works and an answer to our inquiry under our assumptions about how the world works. But then the world intervenes and causes data to emerge. So from our data strategy, a data set is constructed. That data set is affected by our interventions into the world, D, but also how the intervention by the world. How does the world realize this data? Then that little d data set causes an answer, so an estimated average treatment effect, maybe 0.05. That's a function both of the data, which is again a function of of the world and of our data strategy, and it's a function of our answer strategy procedure. So AD is our answer, our estimated average treatment effect, which is a function of our answer strategy and the data that results from our data strategy. And the goal of creating a great research design is that we want to have parallelism between these two pieces. So we want a data strategy that mimics how the world works as closely as possible, and an answer strategy that provides a parallelism to the way that the inquiry yields the true answer. So we want an average treatment effect estimate that is as close in its functional form to how the inquiry yields a true average treatment effect from this model of how the world works. Okay, so I'm going to take this out of the theoretical and into the practical. How do we actually do this? You could declare your research design in terms of its model, inquiry, data strategy, or answer strategy using any programming language, and you could also do this using an analytical formula. We developed an R package called Declare Design that allows you, that implements this language for research designs in R. So this is what a simple research design looks like. So I'll walk through each element. So we start out with the model. Again, the model defines our view of how the world works, what causal variables there are, and how they're related to each other. And so we have that causal variable x. So it's a binomial random variable. So R banam is the R function for generating a binomial random variable with a probability of 0.3. Then we have unknown heterogeneity in the world, and that is distributed as a standard normal random variable. We define here that we have a population of units of 100, and we're going to treat that population as the sample. So we won't have any sampling here. We're going to conduct measurement on all 100 of those units. The second piece of the model is how outcomes are generated from our causal variable of interest, which is z, and also these other causal variables x and u. So our outcome variable y is going to be a function of z, the treatment variable, x, that covariate that we're going to block on, and then u, that unknown heterogeneity. And so here we're introducing our assumption about the expected effect size, and we're saying that that is a function of these causal variables. The second piece is our inquiry. In this case, we're going to run an experiment, and our inquiry is going to be the average treatment effect. So the average treatment effect is the average, so the mean difference between the potential outcomes. So potential outcomes are how outcomes respond to treatment. So we can imagine what outcome each unit would have received if they were assigned to treatment, and what outcome they would have received if they were assigned to control. Obviously, each unit is only going to be assigned to one of those two conditions. And so these are potential outcomes because they are what could have potentially happened if they had been assigned to these two different possible treatment conditions. And so the average treatment effect is the average difference between the treated potential outcome and the control potential outcome. These are theoretical. These are based on our assumptions about how the world works. And so they're based on suppositions. We could have made different suppositions, and it's going to be important to assess how robust our research design is to those different possible assumptions.
I'm sorry to interrupt.
Yeah, go ahead.
We have a question from Jonathan Hirsch. He's asking, how do we decide what covariates we want to include in our block randomization?
That's a great question. We want to select covariates that are predictive of the outcome. So we want to form groups that are as similar to each other as possible. And then we want to assign the treatment within those blocks of most similar units. And the reason for that is then we're conducting experiments within groups that are otherwise very, very similar by construction. And so we want to guess what covariates that we can measure before the treatment are going to be most predictive of the outcome so that we can construct blocks that turn out to be very similar in terms of the ultimate outcome that we're going to be interested in. But because we have to do that before the treatment is assigned, that involves some guessing and use of past research to understand what covariates are going to be related to the outcome. That's a great question.
And we have a couple of follow-up questions. Sean Lahiri is asking, is your view of potential outcomes akin to an intent to treat approach?
We can declare a design that involves, so basically the question, intent to treat is a way of thinking about about the problem of noncompliance. And so what we've written down here is that the outcome y is a function of z, which is the treatment that we've randomly assigned. But often when we're conducting field experiments, the treatment that people actually receive isn't the treatment they were assigned to. And so, for example, our treatment might be knocking on someone's door, but they might not answer the door. And so we might want to think about those as two different things, being assigned to have someone show up at your door and having you actually open the door and talk to someone about voting for Joe Biden, for example. And so we can declare a different design to assess what the risks to our design are from the divergence between what you were assigned to and what you actually received. And so you could set up two different sets of potential outcomes that are you would have a first potential outcome that is, how does whether you talk to a canvasser respond to whether you were assigned to talk to a canvasser? And then a second set of potential outcomes that are, what is your vote choice as a function of whether you actually talked to the canvasser, which is the treatment that we think actually matters. That's a great question. So it's not hard coded into here, and that's something that's an important breakdown of experiments that we'd want to know, is our research design good enough for that?
And one more question from Jonah, I'm sorry, I'm not sure about the pronunciation of this name. Does this translate to more complex experimental designs, such as, for instance, those with spillover effects or conjoints?
Definitely. So those are both like complex to declare, not in our framework or any framework, but you can think about spillovers are also a different form of potential outcomes. And so the assumption of we're invoking an assumption of no spillovers here by saying that potential outcomes Y are only a function of Z, your own treatment status. Spillovers would be a situation where your potential outcomes are a function of other people's treatment status. And so we could set up our potential outcomes so that it was a function not only of whether I was assigned to someone coming to my door, but whether my next door neighbor was assigned to receiving a door knock. And so you can imagine that someone, if your next door neighbor's door is knocked on, then that might also trigger you, if you saw that person coming up to the door, to remind yourself that you need to go vote. So you could imagine that that would affect your outcomes. So we can incorporate that by allowing for having a Z variable, but also Z neighbor variable, for example. That would be relaxing the no spillover assumption, allowing for a particular kind of spillover from the neighbors. And we can think about a million other kinds of specific violations of the no spillover assumption. And in terms of conjoints, we have a template for a conjoint. They're complicated because a conjoint is basically like where you're asking people to vote for you present people with two different candidates that they could vote for in a survey, and then you randomize all of the different characteristics of those candidates. And so you have a candidate that is described as a 25-year-old woman who is a lawyer and who is from Santa Barbara, and a man who's 34 and who is an engineer and is from Santa Ana. And you randomize all of those components and then try to understand what's the impact on which of those two people you choose of those characteristics. And so we can incorporate that by having potential outcomes that are a function of your age and where you're from and your profession. And your data strategy would involve randomly assigning those people to each of those characteristics. So we'd have a different treatment variable for each of the characteristics that we randomized in the conjoint.
And then one final question from Maria. She's asking, can you discuss optimal number of covariates for block randomization? Also, trade-off between predicting outcome and degrees of freedom.
So I think all of these questions are questions that are the kinds of questions that Declare Design is designed to help you answer for yourself in the context of your own particular research design. And so the question of how many covariates to control for isn't one that I can answer generally. It's one that you would want to answer in the specific context of your research. And so you want to do something like set up two different designs, one that had 25 different covariates, the specific covariates that you imagine measuring, and your suppositions about how they're related to the outcome, and then compare that to a design that only had one or two that you've chosen to be, that you think are really highly predictive. And you might use Declare Design in that setting after you've conducted your baseline and before you conduct your treatment assignment, and you could compare those two designs using your actual data. So instead of using a mock population here, you could actually put in your baseline data, and then the only part you would simulate were the potential outcomes and the treatment assignment. And you could ask the question, which of these two designs is better? The one that I put all 55 variables that I collected in my survey, or these two that I particularly selected? And it could help you answer the question, which of those two is going to be better.
Awesome, thanks, Graeme.
Okay, so with this design, we can do a couple of useful things. First, before diagnosing the quality of the design, the first is we can just draw simulated data. So this is simulated data that I drew last night from this design. And so there are 100 units in here. They have an X variable drawn from that binomial distribution, a U variable drawn from that standard normal. And then we have these two potential outcomes that are drawn as a function of, as that function of 0.1 times Z plus X plus U. So we have both the treated and controlled potential outcome. Of course, those are unmeasurable. Those are potential outcomes. We only get to realize one of them, but in this framework, we can think about what those potential outcomes, we can imagine what those potential outcomes would be, which is useful for diagnosing the quality of our design. Then we have a simulated treatment assignment. We have the conditional probability of being assigned to that treatment condition. So if you noticed here, we're using block random assignment, and we're setting the block probabilities here to 0.1 and 0.5. That's the probability of being assigned to treatment in the two blocks. X is 0 and 1, so the probability if you're in X equals 0 of getting treatment is 0.1, and if X equals 1, it's 0.5. So that's the probability of being assigned to the treatment condition you were assigned, and then we reveal the outcome. And notice that revealing the outcome is basically just taking these two potential outcomes that we defined, and then picking the potential outcome that would be revealed under that treatment condition. So for unit number 1, the control condition, it was assigned to the control condition, and so we pull the control potential outcome 1.66, that's the outcome. For unit 2, it was assigned to the treatment condition, and so we pull the treatment potential outcome negative 0.59 as the outcome. So this is simulated data. This is really useful because it allows you to try different estimation strategies. So you can imagine what your data is going to look like before you actually collect it. Second, we can draw estimates from that design. And so this ran the linear regression that is implied in this answer strategy. So we had a linear regression of Y on Z. And so our estimate is 0.64 with a standard error, a t-statistic, a p-value, and a confidence interval, the lower bound and the upper bound. We can also draw the estimand, the average treatment effect, that's 0.1. So the way that calculated it was it took the average difference between YZ1 and YZ0 in this data set, that's 0.1. That makes sense given that we defined our expected effect size as 0.1. Okay, so we can draw estimates and draw estimands. And so now we're ready to put together this language for research designs into an algorithm for selecting designs. So that algorithm is going to be in 3 parts. So I just introduced a language for declaring a design, that's step 1. Step 2 is diagnosing the design, that's assessing the properties of that design. And step 3 is redesign. So if we don't like the properties of the design, we're going to redesign them. So now I'm going to introduce the next 2 steps, starting with diagnosing. So diagnosing a research design is answering questions about the properties of research design. So is my design powered? Is it biased? Does it provide value for money? How likely are we to get the sign of the effect correct? And there are two ways to get at this. The first is we can use analytical expressions from a textbook. And the second is through simulation, by running our design under a set of assumptions about the model and the inquiry, running it over and over again, and then calculating those properties from the simulated data sets. So the traditional way of doing this uses analytical functions, analytical expressions, and online power calculators are all based on some version of this kind of analytical expression that comes out of like a high school stats textbook. It turns out that these analytical expressions are actually making a ton of assumptions about what research design we're actually running. So this power formula makes detailed assumptions about the model, the data strategy, and the answer strategy. So in terms of the model, it assumes that both potential outcomes are normally distributed. That's coming from the fact that we've assumed this symbol represents the cumulative distribution, the normal cumulative distribution function. So we've assumed that there's a normal distribution here of the outcomes. That may or may not be true. And we've assumed that there's a common variance. So here we have sigma, which we've assumed away the possibility that there might be a different variance in the treatment group and a different variance in the control group. In many circumstances, when there are heterogeneous treatment effects, that will be false. In terms of the data strategy, it assumes that there's a particular randomization strategy, which is simple random assignments. So for example, in the example that we've just set up for block random assignment, that would be wrong. It assumes a particular hypothesis testing approach, that there are equal variance t-test, and a particular degrees of freedom, n-2. And so this set of assumptions may be close enough in some settings, but it can be really difficult to understand the specific impacts of different beliefs about M, D, and A on the value of power, for example. So in ours, what if instead of being normally distributed, the potential outcomes are measured in 1 to 5 Likert scales? What if the randomization procedure includes blocking like ours did? And what if we included covariates in our treatment estimation approach? All of these things may have an impact on the power, but wouldn't be reflected in this power formula that's used in all these kind of online power calculators. So relatedly, power is just one diagnosand that we might be interested in. The second is their bias. I think the way that we often think about is our design biased is by thinking about different particular situations that we've read about in textbooks or in methods papers that are biased. So we can think of lots of those. Blocking with heterogeneous assignment probabilities is biased. Random assignment of clusters with different sized clusters can lead to bias. When attrition is a function of treatment status, logit with fixed effects, post-treatment bias, we can think of lots of situations where design will be biased, may be biased in general, depending on the features of our design. But how do we find out if our design is biased? We have to know in advance that our design has a problem that's identified in a textbook or recent methods paper, and we have to know that it applies in this particular setting. And so many kinds of bias are of the form in small samples. There will be bias, for example, from instrumental variables estimation. But how do we know if we're in a small sample? We only have one sample size that we selected, 100 here. How do we know if there's going to be bias? It's going to be hard to figure. Textbooks are not going to provide an answer to that question. Skip that. So design diagnosis provides a tool that allows us to assess for our design in our setting, what are the properties of the design? And so I'll kind of illustrate how this is going to work. So we start with one run of the design. This is just going to put together those two functions I showed you before that draw the estimates and that draw the estimand. And we'll put those together. So we get the simulated results from one run of the design. And so let me illustrate those graphically. So this is taking these estimates and putting them on a graph. And so we can, there are a few features that are important here. So we have an estimate, that's the circle. We have a confidence interval, so that's the confidence interval. And then this is the estimand value here that comes from that run of the design. There's an implied t distribution from the estimate and the standard error, and the area under the curve here to the left of 0, and then the parallel area over here is the p-value. So from this, we can calculate important, what we call diagnostic statistics, which are just functions of this run of the design. So for each run of the design, we can calculate the estimated error. So the error is just the difference between the estimand and the estimate. So for each run of the design, we can calculate things like error. We can calculate the p-value for each run of the design, which is important for calculating statistical power. And then we can run the design over and over again. So we're just going to run that function, run design over and over again, 1,000 times, for example. So we get 100 different estimates, 100 different estimands. I've added another line here, which is the average estimand. So that's going to be, in this case, about 0.1. And then we can summarize those runs of the design. And in particular, for each of these, we can calculate the error from each of these runs of the design, which are going to vary each time because our estimate, and in this case, our estimand, are varying very slightly. So from that, we get a data frame of simulations. We get a data frame of estimates, standard errors, the lower bounds of the confidence intervals, the upper bound of the confidence intervals, p-values, and the estimands. And then it's just a data set. And so we can summarize that data set. So we can calculate what we call Diagnosands, which are just summaries of these diagnostic statistics or summaries across these runs of the simulation. So we can calculate bias. Bias is the average error. And so we calculated error a minute ago as estimate minus estimand. And so bias is the average estimate minus estimand. We can calculate the root mean squared error, which is taking the squared errors. So that's allowing for errors to be positive or negative and kind of ignoring that. Taking the mean of the squared errors and taking the square root. And that's going to be a good measure of the trade-off between bias and efficiency of the design. We can calculate the power of the design by taking the proportion of times that the p-value is less than or equal to 0.05, what's the proportion of times that we reject the null hypothesis. And we can get the other kinds of quantities that may be important for theory testing, for example. So we might be interested in this design in the probability of getting the sign wrong. So we're not interested maybe in the magnitude of the effect, but in the sign. And so we can calculate the proportion of times that the sign of the estimate is not equal to the sign of the estimand. Okay. Sorry. So just to give you a little bit of intuition about how we might select those, these are 3 different archery targets. So we can think about 3 different designs that might have different properties. So in this first design, this has really high variance, but is unbiased. So there is, we're getting estimates all over the board. They're really far apart, but they don't seem to be particularly, they seem to be centered on the truth, which is at the center here. The second design is unbiased, and sorry, these labels are off. This is unbiased and precise, and we can think about a third design that is biased. It's far away from the truth here, but is really precise. And so clearly we're going to want to look for a design that is unbiased and also as efficient as it can be. And the second point to make is that where this center point is on these archery targets is defined by us as the researchers. We've defined what the inquiry is and where we're shooting at. If we had defined that differently, we would have gotten a different answer in terms of bias. And so there are 2 targets here. This design is really good at targeting the estimand on the left and really bad at targeting the estimand on the right. And so we can think about, we want a design that is efficient and unbiased and is shooting at the target that we're interested in.
Graeme, a quick question from Olavi. Is asking, won't the simulations be dependent on the assumptions of probabilities we made at the first stage? How would we know exact values to do such simulations?
Great. So that's a great, important question. We don't know them, and that's part of the reason that we're doing the research. But in order to assess the properties of the design, we're always making these assumptions. So I went through that power, the equation for the power calculator. There we have to make assumptions about the expected effect size, about the variance of the treatment and control groups, and those are assumptions that could be wrong. So any power analysis is dependent on the assumptions that go into that analysis. So part of the point of declaring your design in this way is that you have to be more explicit about the assumptions that you make, and you can move your assumptions closer to what you think is probably true. But they're always going to be wrong. That's the purpose of running the research. But in order to assess whether our design is a good one from before conducting the research perspective, we have to make these assumptions. That being said, it's not the case that we can't get better at those assumptions. There are lots of sources of information and data that can help us improve those assumptions that we make. We can use baseline data that would give us the exact distribution of those variables if we have baseline data. We can use data from past studies to learn about the correlations between variables and how they're distributed. And we can conduct pilot studies to learn about some parameters like the standard error of the estimate, or the standard deviation of our outcome could be usefully learned from a pilot study.
Thanks.
Okay, so we're going to diagnose a design. This is a quantitative estimate from simulation of a set of Diagnosands. So I took that design that I showed you and diagnosed it. So we get a bias of 0.5. That's absolutely enormous. The estimand is 0.1, so a bias of 0.5 is really bad. That's 5 times the estimate. we get a root mean squared error value. This isn't going to be especially useful except when we're comparing two designs. We have a power. Our design appears to be underpowered. But note that when a design is biased, the power, we're in a situation like this where we have a really efficient estimate of the wrong estimand. So we're not really interested in the power for that biased estimate, and we can calculate the probability that we get the sign wrong. So this is research design diagnosis. And so in our algorithm for selecting designs, the algorithm is in these three parts. We're going to declare a design, we're going to diagnose it. In many cases, we're going to find out that we don't like the values of the Diagnosands. We think the design is not good enough. And so we're going to redesign the design and then redeclare it and then diagnose it again and do this over and over again in an iterative process until we're happy with the values of the Diagnosands. And so I'll just illustrate that for you briefly here before we open it up for questions. I'm going to redesign that. Oops. Great. I'm going to redesign that design. So I have this design. So this design is highly biased. The reason for that is that we have different probabilities of assignment in these two blocks, and we haven't accounted for that in our estimation strategy. And so there's two ways that we could fix this. One is we could just change the block probabilities. So if I do that, I can make the block probabilities equal across the two blocks. Then I don't need to control for them. So I can redeclare that. I can draw the data. So there's 100 units in the data. I can draw the estimates. I can draw the estimand, still 0.1. And I can diagnose that new design. That new design is unbiased. It has really bad power, so I might want to increase the number of units. The other thing that I could have done is, instead of, if I think it's important in this one group to have a low probability of assignment and the other group to have half and half, then I could adjust my answer strategy. So I could switch to using a weighted regression where I weight by the block probability. So going into my data, I know that I have in my simulated data, I have the conditional probability of assignment of 0.5 or 0.1. And so I can weight by that conditional probability. So I keep the block probability as the same, and I weight by the inverse of that probability to upweight those that have a low probability of assignment and downweight those that have a higher one. And so I can diagnose that design. And that's also unbiased. So there are two different ways that we could have adjusted this design. So when you run your design, you're often going to find that unexpectedly there was bias or there's really low power, and then you can change different features of the design to address that. Here again, we have really low power, so we may want to increase our sample size to 1,000. So I can run the design again and diagnose it again. It's going to take a little bit longer because it has to draw a data set of 1,000. Power's gone up a little bit, but not a huge amount. This is a relatively small, our expected effect size is relatively small. And so we're going to have to get, what this process is telling us is that we're really going to have a really huge data set. We're going to have to run a huge experiment in order to answer this question.
A quick question from Sharada. Is asking, when redesigning, is there a way to keep track of the evolution of the design?
I'm just going to stop sharing and we can open it up for more questions as well. Is there a way to keep track of it? I guess what I usually do is if we were looking at this particular version of the design, I might be interested in how does this design change across a bunch of different sample sizes. So I might be interested in, like, what is the power of this design for at 100 units, at 1,000 units, at 3,000 units, and I could use there's an expanded design function that will create a bunch of designs for you, and then you can diagnose them all at the same time. I think the other thing you could do is use GitHub use a version control software. That's what I typically do, where I have the first design and then all of the little iterations, and then often I'll have to go back to an earlier version because like the design diagnosis is very multidimensional. Like all of these different choices that you're making as a researcher interact. And so often I'll have to go back to some earlier answer strategy, for example.
Awesome. Luckily, they will learn about GitHub tomorrow. So
Awesome.
Immediate application here. We received a couple of questions earlier during your presentation related to declare design in general. Hayojai asked, is there any plan from the declare design team to add some kind of design visualization function into this suite? Sort of like Lavon, etc., have been doing for different things.
Yes, we have a function that we just made about 3 weeks ago that basically produces a DAG for your research design. I find it extremely helpful. It prints a DAG like that first one that I showed you was created using this function, and so it shows you it has a different symbol for random assignment, measurement, and sampling. And then it has all of the causal variables that come out of your population and potential outcomes, and also how they relate to each other. Because everything in the design declaration tells you how Y is related to Z and X, we can put together that graphical representation, both of how the variables relate to each other and which parts are being manipulated by the researcher and which are just being set by the world.
Thank you. Shawn asked, I'm thinking that this package would be great to see what the outcome might look like under different prior distributions in a Bayesian design. Can declare design accommodate Bayesian priors at the moment?
So it can accommodate any answer strategy. So I would answer your question in kind of 2 ways. One is a Bayesian answer strategy would have priors and a likelihood that would translate the priors and the data into a posterior. And so we have an example of that, I think, on our website that uses Stan. It's a little slow because you have to sample in declare design and then sample in Stan. But the other thing that I would say is to the earlier question was about, there's an earlier question about how do you know how to set all of these, how to set all of these distributions? Like we don't know. And one way to use declare design is to say, like, I really don't know what the distribution is here or what the expected effect size is. And so I'm going to diagnose my design under all of the possible scenarios. I want to know whether my design is any good under an expected effect size of 0 all the way up to a really large effect size. And you could do the same thing for what is this going to work under a binomial distribution for X or under a normal distribution for X. And so instead of thinking about it as like, I have to get these parameters right, is my design going to be good under the range of all the different possibilities that are plausible?
Great. We don't have any current questions in the chat so far, but I would like to encourage everyone, if you do want to speak up, you can unmute yourself or raise your hand and I'll unmute you. You can ask questions or comment that way as well. And we have about 5 more minutes for discussion.
I have a question.
Yep, go ahead.
Will the breakout session that's coming up on experimental design be more on this, or will it be a little bit more big picture structural questions? Or
we're going to reverse engineer an actual experiment and write a pre-analysis plan for it. And some of it will be in declare design, and some of it will just be thinking about how to write a pre-analysis plan.
Thanks.
Oh, I have a quick question. Yeah, I'm just wondering, do you have examples of a pre-analysis plan that's currently been published that has this information from declare design in there already, just to get a sense of what that kind of looks like?
There's a few of them, yeah. I'm happy to. I'll put some links to them in the OSF after the session this morning.
Thanks.
We just got a question from Ruben. What is the best way for us to practice declared design? Reverse engineering a PAP?
I think the best way to practice is actually using it in your own research. That's how I found it to be useful. That's how I've learned it myself. Is planning little like taking every little decision that I have to make in a research design. And when people ask me research design questions, instead of trying to speculate about them or go back to the textbook, I try to write down a design declaration and then diagnose it. And often through that process, I often discover pieces that I hadn't thought about, or when I'm talking with a graduate student about their research design, it leads me to ask questions about their design that they hadn't thought of before, and to try to specify pieces of like how they're thinking about how the world works and specifics of their data strategy, for example, that they might not have otherwise had to think about before getting the data back. When a lot of those decisions are kind of set in stone already.
Just another question just came in from Shabano. She's asking, are there rules of thumb for what the expected effect size should be, or what effect size we want to see?
I think it's really dependent on the particular study context. And so I think like, how should you select an expected effect size? I think there are a couple of answers to that. One is you want to read the past literature and understand what past effect sizes have been. And so where there are meta-analyses that exist, those can provide really clear guides for both what average effects have been in past studies, but also like how widely distributed there are. Like, are these pretty consistent in the past literature, or does it really seem to be context dependent? Both of those might help you decide an expected effect size or a range of expected effect sizes that seem to have obtained in past literature. And so then you would want to think about a design diagnosis that looked at all of those different possible effect sizes. So I think in general, you don't want to think about a single effect size, but what is the range of plausible effect sizes? And when there isn't past literature, or when people haven't done a meta-analysis and you don't have time to, I think what you want to do is think about how your design is going to perform under a best case scenario and under a worst case scenario. And so you can think about what's the largest plausible effect size, maybe even implausibly large effect size, and what's the smallest plausible effect size, something really close to zero. And then how's your design going to perform under those different scenarios? And I think that's kind of general. That's not, none of that is specific to declare design, but how to think about research design planning in general.
I think I was muted. Thanks, Graeme. I think we have time to do one more quick question, and it just came from Awaz. He's asking, how well does the package handle cases involving complicated DAG situations such as independent variables?
Instrumental variables.
Instrumental variables, sorry.
Yeah, we have an example of instrumental variables and encouragement designs that use instrumental variables in experiments on our website. It's complicated. You have to set up a complicated scenario, but I think that like it's complicated to think about instrumental variables scenarios in general, and so I don't think there's any added complication to it. I guess the one other thing I would say in closing is that I think this like planning for your research design is not something that necessarily must be connected to a pre-analysis plan. This is a set of procedures, whether you use declare design or not, that help think about how should you plan for research and make the many choices that you have to make, both before you go into the field in data collection, whether it's quantitative or qualitative, and what you do once you have started the research and you're faced with the many decisions that come as you're collecting data when things are not going according to plan. And so I think this is, whether you use our tool or not, we think this is a way of thinking about how to assess those choices, both as you're writing a pre-analysis plan, as you're conducting the research, and then as you're assessing what happened afterward. and comparing your planned research design to the design that you actually implemented. And thinking about what you can learn given all the changes that we all make in our research after we start implementing it is hard. And this is one way of thinking about how to compare your planned design to your implemented design. So thanks for listening.